this video, we are focusing on the concept behind linear regression. Here we have two basic types, which means simple linear regression model and the multiple linear regression model. First, discussed about simple linear regression. There we can write down the model as y equal beta 1 plus x. So in um, basic terms, but for more clarity we can add this index I and the epsilon or the random error term. So this is the simple linear regression model. Let's visualize what's mean by this. So here we have two variables. So x is the independent or the predictor variable, y is the dependent or the response variable. So both x and y are quantitative variables. So beta 1 and beta naught are the parameters of the model, and epsilon is the random error term. For the simple linear regression, you can say this is y and this is x-axis. So in every sample we have several levels for x. Let's say x1, x2 and x3. So for this x1, suppose we have observations like this. Y1, x1, y2, x1, y3, x2. Likewise, we can have different y values for same x level, like this. So these are paired observations. So in regression, we are going to find the form of the relationship. Unlike in correlation, there we find the type of the relationship. So the regression is causal, but correlation doesn't show the causal relationship. It just shows the type of the relationship. But in here, we say for each x level, suppose it is x1, we have a separate distribution for y. So we have a distribution for y here. And for the next x level as well, we have another distribution for y. And for x3 as well, we have another separate distribution for y. So the true regression line is formed by connecting the means of these distributions. So suppose for this one, mean is located in here. For this one, in when x equal x2, the distribution of y has a separate distribution, but its mean relies on this point, and here we have this point. So the line connects here this should be the mean, this should be the mean, and this should be the mean. So this true regression line is formed by connecting the means of these distributions at each x level. So these are conditional distributions. So which means the distribution of y given x. So this is the expected value of y given x1, and this is the expected value of y given x2. So likewise, the true regression line can be taken by connecting these expected value of separate distributions of this y. So this is the overview of the simple linear regression model. So this is the true model. So to have this true model, we have to have more observations or more responses for each x level, which means we need to have few more observations of y when x equal x1. Likewise, for each x level, we need more y's. But in the practical world, we have only one or two observations for each x level. Most probably, they are coming with paired observations, which means for each x level, we have only one y value. So then we can't find the exact mean of the value. So we have to make an assumption to build a model. So there, suppose I have a sample and my sampling point is here, another point is here, another point is here. So I have only three observations uh, here: y1, x1, y2, x2, and y3, x3. Then you can see at each x level we have this type or this much of error. If we take the difference of the actual observation with the actual line. So that's why we put an random error term. So since this is a probability distribution and we take the sample from random process, we don't know where or the location of this distribution. So this error is random term. So that is why this regression line is different from the linear equation we know y equal mx plus c. So here these are constants, but in here these beta 1 and beta naught has separate distributions as well as eta has separate one. So these three parameters, these two parameters and this random error term has probability distributions. So which means we connect probability with the data, and that enables us to take a summary of the data set or the parameter prediction, and we can use these lines for take predictions or control the process. So like in quality control, so we can use these regression, so taking a sample and by modeling a regression line, so you can understand the process and you can predict depend on the probabilities of these distributions, and you can control the process depending on the information grabbed from the sample. So those are few examples of uses of regression. So this is the explanation. So in simple linear regression, we have only one x or one independent and one dependent variable. So here, to build this regression line, always we can't always we predict this or we estimate these parameters, since we can't find the exact value of these parameters, which means for each sample from the same process we can have different parameter estimates depending on the sample values, which means we are taking the fitted line, not the actual line. So the fitted line can be something like this or something like this, but this fitted line and the actual line always go through the point of y bar and x bar, which means taking the mean of these x's and taking the mean of these y's. For more clarity, we can refer this graph again. So this line is yi plus beta naught plus beta 1 xi. But in our case, our actual observation is somewhere here. So, which means we have an error term in here. So this is x1, x2, and x3. Suppose this is epsilon 3. So here we have an observation here. So it is epsilon 2. And here it is epsilon 1. So using this line, so I can represent this point as yi or y3 equal beta naught plus beta 1 x3 plus epsilon 3. So likewise, each point can be represented through this line, which means this point plus the random error component. That is why this is important. But most of the time, we take a sample, and because of that, we always find an estimated line. So can be something like this. Then this estimated line is written like this: beta naught hat, beta 1 hat, and xi. And now we don't have any error term because these hats are the estimates from the sample. So to estimate these hats, we can use any point estimation method. So most of the time we use least square methods to derive the estimators and take the estimates for beta naught and beta 1. So least square methods means by taking this true regression line, we try to minimize the square sum of errors. So then we can find the estimators for beta naught and beta 1. So as I showed you, this part is now a constant, and this is the random part. Since you can see in this line, beta naught and beta 1 are parameters, but they are constant, and x's are predetermined, which means for each x levels y has a separate distribution, which means at each x level the total or the summation of these two terms are constant. This is the random part. So we can make few assumptions on this random part. Then we can move on to the estimation part depending on this assumption. So there we can say, first we have to identify that expected value of y is none other than this. So if this is since this is a constant, so then to have this expected value of error term should be equal to 0, and we say these, though they have different means, the variance of these distributions are same. So then the variance of the error term is also same, and these errors are uncorrelated, which means the correlation between any random error terms are equal to 0. So these are the assumptions we have to make regarding this error term. So then we can move on to parameter estimation. So most of the time they are using this random distribution, or we consider this random distribution of the random error term as a normal distribution. So then we assign that this error term is normally distributed with zero mean and sigma square variance. So those are the things that we need to know about the basic of this regression model. So depending on these cases, we can have the least square estimates for beta naught and beta 1. So then we can see the estimators for beta 1 and beta naught. Now we know this is the true regression line. So since we are using this least square method, so we can use summation of the squares. So this is the equation. So we can minimize this part, which means take this part as another y and minimize this equation. So by doing that, we can have estimators for beta naught and beta 1. Then for the estimator of beta 1 hat, so we can write down x minus x bar times y minus y bar over x minus x bar square. And also using this, we can show the naught is y bar minus beta 1 hat x bar. So these are the estimators, and using these estimators, you can substitute the sample values in here and take these estimated values. So now you can have the estimated line. So this line depends on the sample data. So which means these two estimates are coming from the sample. So now we don't have an error term, so we have a residual. Still we have uh, some sort of error, which means there is a gap between the actual data point and the fitted line. So the gap between the actual data point and the true line is the true error. But here, or the error term of the random error component of the system, but here we have a fitted line, so the gap between the fitted line and the actual observation is equal to the residual. This residual can be written like this. So which means this is the y in your data set. This is the y you can take by substituting your x values in using these estimates and calculate the y hat value. So this is the residual. And at the same time, by using these cases, you can find an estimate for sigma hat as well. So it is vi square over in minus 2. So now we know an estimated value for sigma square, beta naught, and beta 1. So this is simple linear regression. So when it's come to multiple linear regression, we have more independent variables. So, and we have to deal with uh, this sort of estimators, but it is easy to use matrix algebra to deal with those high dimensional arrays, which means here we have more independent variables. So in this system, we have 3 independent variables and a random error term and this. So this is the multiple linear regression model for 3 independent variables and 1 predictor variables. So there we use the matrix notation to make the calculation easier. So I can say this is y, capital Y, and we have n observation, so it is like this. Now it is a matrix, and here we have 3 independent variables and for this beta naught parameter, we can assume that we have one always, we have a 1 here. So then you can say this is the capital X matrix, and the dimensions of this is we have n observations and columns. So in rows and 3 variables plus 1. So which means 3 plus 1 columns. And the multiplication with beta, where we have 4 parameters. So 4 times 1. So here it is 4, and plus epsilon, where n times 1. So the error term, more generally, it is independent and identically distributed with this. The assumptions that we made for the error term in simple linear regression is valid for this multiple linear model as well. So for more generally, we can write down general multiple linear model like this. Yeah, we have p independent variables, and error term is normally distributed like this. So we can write down it in matrix form like this. So here n times p plus 1 beta p plus 1 times 1 and n times 1. So this x is like this. 1 for the first column is full of ones, and the second column is data from x1, the third one is data from x2, and the last column is data from xp. So it's like this. And y is just the observations of y1, y2, y3 up to yn. And beta, we have beta naught, beta 1 up to beta p. And for errors, we have epsilon 1, epsilon 2 up to epsilon n. So these are the matrices. So this is the formation that we use to solve or form the multiple linear regression model. So even for simple linear regression model, it is easy to use this matrix form for calculations, but the estimators are still in the same way, which means we can derive estimators for beta matrix directly by using that concept, least square concept. So let's see what are the estimators for these betas. So by applying the same approach we use in the least square estimation, we know that beta is like this, and our beta hat should be like this. So it is a matrix with estimates. So I can take this x transpose x inverse x transpose y. So this is the estimator for these sets. So you in each element in this matrix is an estimate for each parameter. So that is the simple overview of linear regression.